Hello and welcome to Alkenes 8. This is the last proper sort of lesson in this sequence. There is an extra lesson, but it's not going to fit in this playlist because it really requires you to be in year 13 and have studied some further organic chemistry, but it's kind of a review of certain things in this topic. This is the last one, okay? We could actually find this sequence of chemistry, this reaction that we're going to look at, in the alcohols topic as well, because it really has to do with the production of ethanol. It's a method of production of an alcohol, but it is a reaction of an alkene, and so there's also no reason we can't look at it in this topic. So it's a bit of a funny one. We'll come back to it again in the alcohols topic as well. So this is all about hydration of ethene, sometimes called direct hydration. Okay. Let's start with some starter questions as usual. Okay, not loads to go out this time. Unpick the polymer diagrams to show the monomer structures and define displayed formula. Pause the video, answer the questions. Okay, so, right, unpicking the polymer structures, what we'd have is something like that for the first one. That's actually butene, okay? It doesn't matter if you've pointed your methyl groups upwards or downwards, it's completely irrelevant. I've just pointed them to the side because that's how I'd normally draw butene, okay? But obviously the polymer that this was made from was polybutene. Again, the idea here is that you're focusing your attentions on that middle section and realizing that when the polymer was formed, the double bond that was between those two carbons had broken, and the carbons had formed bonds, trailing bonds outwards to polymerize. And so if you're doing this process in reverse, then what you should do is get rid of the trailing bonds and put the double bond back where it was between those two carbons. And as usual, everything else within the structure stays the same, right? So the monomer below, styrene is the name of this because the polymer that it comes from is called polystyrene. I guess this would be called properly phenyl ethene. You'll learn about that a little bit more in year 13. Don't worry about the scary looking ring structure. It really doesn't matter because no matter what you're doing with polymers, if you're just looking at what's happening in terms of the addition across the, from the double bond when it polymerizes, all the stuff that's attached to the carbons is it's not totally irrelevant, but it doesn't really matter if you understand it or not, right? You just replicate it, either when you make the polymer diagram from the monomer or the reverse, which is what we're doing. Same thing for the third one, okay? Again, I'm not even sure how I'd go about naming this at the moment. It doesn't really matter. But again, we've just taken it, remove the trailing bonds, remove the N, remove the brackets, and there you go. Then displayed formula, not one you'd typically define. It's not something you usually ask for a definition of because most of the time when you're exhibiting your understanding of a displayed formula, you're drawing one. So it'll say, draw the displayed formula of insert molecule here. But if you were asked to define it, the best way to sort of describe it is it shows everything. It shows all the atoms and all the covalent bonds in a molecule. That's the best way to think about it. All right. So then, only a couple of bits and bobs for start there. Let's push on and have a look at the hydration of ethene. So here are the facts, right? Quite a lot to take in here, okay? Pause the video and make your notes and then we'll talk about it. Okay, so the first thing to sort of clarify is that there are several different methods of manufacturing ethanol. There are two main ones that you need to know about. One of them is the hydration of ethene, which makes ethanol. The equation along the top is supposed to show that ethene, which would be a gas, definitely at these temperatures, is mixed with steam. So we've got H2O gas that represents steam because the temperature is well above 100 degrees C, and it will make ethanol. And again, ethanol's boiling point is about, 70, 75 degrees C. So that would also be a gas, although that's probably the least important state symbol in here. Okay. So you mix ethene with steam at 300 degrees C, that's the usually quoted temperature, in the presence of a concentrated phosphoric acid catalyst. So there are a few things to talk about here. The first thing is, like I said, this is one method of making ethanol. An alternative is fermentation, okay? And we'll look at that in the alcohols topic because it has nothing to do with alkenes. In this case, the starting material is an alkene. right? And this links to a lot of stuff we already know because we're familiar with the mechanism, not this specific one, but the overall mechanism is the same as one we've already studied, okay? And obviously it's an important kind of use of ethene, as well as polymerizing ethene to make polyethene, right, for plastics. You can also hydrate it and you can make ethanol. And that's commercially and industrially important because ethanol is a starting material for other chemicals. It's used as a solvent. There are lots of other reasons why we might need it. The ethanol that's produced by this process would not be ethanol that you would put in alcoholic drinks, okay? Unless there's something I'm missing, you know, you would almost always use a fermentation process to get that alcohol. Right then, so things to talk about. The temperature, 300 degrees C. I've seen that in one or two places. There's probably a range of values because there pretty much always is. But it's a high temperature, and this is something I tell people a lot. If you can't remember, but what temperature a process occurs at, there are very few where you really actually have to get it bang on right. In this case, it's good if you can remember 300 degrees C, but if you can't, high temperature, right? You might get away with it. And the majority of the time, it's going to be a high temperature, okay? So let's have a look at what makes this reaction tick, right? The catalyst being an acid is actually kind of an important part of this, and that's something we need to look at. I suppose I should also point out that it's the phosphoric acid is usually put on some kind of solid or solid support, some kind of inert material. I think silicon dioxide is something they use, but that's not a detail I would bother including in my notes. Okay, let's have a gander. All right. So this type of reaction, we'd class it as hydration because you're adding water to a molecule. The mechanism, though, is electrophilic addition. And we've seen this quite a bit already, right? This is the main mechanism that we look at when we're considering alkenes. Okay, so it's still an addition reaction. It's an electrophilic addition, but you can also class the reaction type as hydration. Just to remind people about this, right? The reaction type and the mechanism type do not have to be the same thing. If you remember back, I don't know, a few lessons ago, we had addition reactions, and then we had the mechanism of electrophilic addition, and they might be the same process, but you can have addition reactions that don't occur via electrophilic addition, for example. In this case, the type of reaction, we're calling it a hydration, okay? But the mechanism is electrophilic addition. Let's have a look at how it works, okay? So the first thing is we need to draw a molecule of ethene because that's what we always do when we're setting up a mechanism with ethene, right? And we've got the double bond very clearly shown. The thing that I've not done is I've not included the electrophile because there's a few things just to think about here, okay? The easiest and simplest way that this reaction mechanism is shown, right, is through using a proton, a hydrogen ion. So what we might do is we might put H plus nearby to that double bond, okay? This is one of the ways that it might appear in the textbooks, and it's a suitable representation for, AS level, year 12 sort of level chemistry, and actually year 13 level chemistry as well. It's fair enough for that. Most kind of undergraduate chemistry courses, anything chemical sciences wise, they would probably have a problem with this because it's not actually very accurate. And the reason for that is that you never really have H plus on its own. It's always attached to something. That's something that I examine in the sort of extra video. For now, though, it'll do, right? It's a simplification, but it's an acceptable simplification. So if you think about how your electrophilic addition mechanism works, normally we would put two curly arrows in this first step. But this time, because the H plus is not attached to anything else, we're only going to need one curly arrow. Okay, we have a region of high electron density, the double bond. We have a positive charge. It's not just delta plus, it's just plus on the hydrogen. So you should be able to suggest one curly arrow and where that's going to go using your knowledge that you've got already. So pause the video and have a go at doing that. So what I hope you did was showed a curly arrow from the middle of the double bond towards that positively charged hydrogen ion. So this might look a bit weird because there's not something below it, right? But this is the kind of method that we use when we're first introducing this mechanism, and it still shows formation of a bond between a carbon atom and hydrogen, right? It doesn't matter whether it's the left-hand side carbon or the right-hand side carbon because ethene's totally symmetrical, right? But we're still forming a bond. So let's have a little look at what our intermediate looks like. Okay, there it is. Okay, and I'm not scrolling down because I just want to wait a second before we look at the next part. There's your carbocation. Whichever way you do it with ethene, it's primary, right? So there isn't any worry about stability of carbocations or differences in products in this process, because whatever you do, you're winding up with ethanol. So in the next phase, right, what we actually have is a water molecule, okay? Because there is, there are water molecules around in the form of steam, right? Gaseous water molecules are around when this reaction's happening. So what we've done is we've formed the carbocation with a hydrogen ion, and now we need another curly arrow, okay? Which is going to show us formation of a bond between the oxygen and the carbon. This, although it looks slightly different to what we've done already, it's still the same idea. So you should be able to look at your notes on electrophilic addition and pause the video and draw another curly arrow. Okay, so here's what I hope you did. A bond forming using the lone pair on the water, one of the lone pairs on the water, towards the carbon with the positive charge. Okay, so we're still not done yet, right? We haven't finished. There's a little more to this mechanism this time. The section on the left is what we would get from that previous step. So remember, curly arrow indicates formation of a bond, right? So if I just go back, we now have a bond between the carbon and the oxygen. That's what the curly arrow represented, remember? Okay. Now, the logic here is sort of similar to something that you have seen before in the halogenoalkanes topic. Because oxygen typically only forms two bonds, when it forms a coordinate bond like it's just done with that carbon, it actually gets a positive charge. And the reason for that is that the two electrons that were attached to the oxygen as a lone pair are now being shared. Well, one of them's being shared with the carbon. Sorry, they're both being shared with the carbon, right? But they both came from the oxygen. So the carbon brought nothing, and the carbon was electron deficient. So that electron deficiency is now sort of transferred, if you like, onto the oxygen. And this is how we represent it. If you're wondering where we've seen this before, we've seen it when ammonia acts as a nucleophile in nucleophilic substitution. It's the same principle. Obviously, it's a different mechanism, but it's the same principle. Okay? So, right, we've got two steps to look at here, all right? Because it's easiest to kind of get your head around what's happening. We have to have some more electron pair movement this time, right? What's going to happen is we're going to, if we play spot the difference, we're going to remove a hydrogen from that oxygen. So one of the hydrogens is going to leave from that oxygen, okay? If you look at the left-hand structure and the right-hand structure, the right-hand structure is ethanol. The left-hand structure is some kind of unstable intermediate that hasn't quite formed ethanol yet. So what we need to do is, let's say it's this hydrogen that we're going to remove. It needs to be removed as H+. It's going to leave as H+, okay? For that to happen, it's going to take nothing with it. So we're going to get a movement of a pair of electrons, right? But we basically have to decide, is it going to go this way? Or is it going to go this way? Okay, that's our option. Because often the movement of a bonding pair basically indicates the breaking of a bond, right? And that's what's happening in this case. The bond between the O and the H is breaking. So let's think about what we just did. We can either put it onto the oxygen or we can put it onto the hydrogen. This is the correct movement, right? And again, if you've looked at your ammonia nucleophilic substitution mechanism, you might see the logic behind this because it's exactly the same, right? This has to do with the fact that we're basically trying to kind of get rid of that positive charge and stabilize the oxygen. And we're doing that by essentially moving a pair of electrons back onto it so that it has the same lone pair or the same number of lone pairs that it did before it formed the bond to the carbon. Okay? The problem with this if we'd gone that way, is that that would make H minus, because what would happen in that case is you're basically moving the pair of electrons onto the hydrogen, which means that H now has an extra electron, which gives it a negative charge. So we want to do the opposite of that, which is why we wound up putting the curly arrow towards the oxygen. Of course, I'm not necessarily expecting you to predict that or be able to figure it out, but I am explaining it because I think it's important in terms of deeper understanding. You can just learn this mech, right? That is one way of doing it. But if you're ever asked to justify certain steps, which you could be in a more challenging question, or if you're ever asked about something that looks quite scary, right? Like some kind of scary looking alcohol, some kind of scary looking alkene, and you have to apply what you know about hydration, it can be easier to do that if you have a deeper understanding. So that's the last curly arrow. The mechanism's finished. There's still a couple of bits and bobs we need to talk about, though. Let's go back up to the beginning. Okay. This proton comes from the concentrated sulfuric acid. Sorry, not sulfuric. They say phosphoric, don't they, for this one? The concentrated phosphoric acid catalyst. If you're wondering why I put sulfuric, it's because often in these reactions, you can actually kind of use one or the other. They both perform a very similar role. But industrially, it's conc phosphoric in this reaction. So that's why I should put CH3PO4. So that proton, that hydrogen ion, comes from the concentrated phosphoric acid. It's not just kind of, hanging around. It's from an acid, okay? So when you put it in at this end of the reaction, it's basically reacted, right? It's formed a new bond and the products are different to the reactants. So at this stage, you can't class the conc phosphoric as a catalyst. But this is a very key feature of many organic reaction mechanisms. When we look down the bottom, right? There's a phrase we use here. We say that the acid catalyst is regenerated. That proton that was donated by the conc phosphoric, it's basically spat out at the end. And so overall, the acid catalyst remains unchanged, which is a key feature of being classed as a catalyst, right? Or the phrase we often use in organic chemistry is we say the catalyst is regenerated, because the idea is that you kind of put it in at one end of the reaction, right? And then some other stuff happens and then it comes out at the other end of reactions. That's what we mean by regenerated. This is a key feature of many organic reaction mechanisms where a catalyst is present. Now, we're done basically. In terms of like the kind of fundamental version, right? That's it, okay? That is the only version you absolutely 100% need. Having said that, right, I am going to just look at another kind of version of this, right? So this is optional, right? Red means challenge. If you feel like extending your knowledge a little bit, then feel free to have a look at these, right? Alternatively, just stop now if you prefer to. So it's your call. So you've been warned, right? The thing that I want to have a little look at is what about an alternative version of the mechanism where we show the acid, right? So here we have ethene. We also have sulfuric acid. Okay, don't worry about the fact it's sulfuric. We'll deal with that after, right? Now, in a weird way, even though I'm complicating things, actually, if we'd done this to begin with, the first step at least would have looked more kind of familiar to you, okay? The reason for that is you're actually aware of sulfuric acid acting as an electrophile already, because you've looked at formation of hydrogen sulfates. That's one of the reactions we did in the first lesson on electrophilic addition. But there's a problem, basically, and that's part of what the other video is about. You'll see what I mean in a minute, if you're still with me. So if you're doing this, you should be able to suggest 2 curly arrows for this mechanism, and it's exactly the same as what you would have had in your notes from earlier in the topic, but then things are going to diverge slightly. What you should be doing is that and that, okay? It's very similar to the standard electrophilic addition mechanism. However, because this is the direct hydration of ethene that we're looking at, the next step, the sulfuric acid appears to have disappeared. It hasn't disappeared. It's still hanging around. The negative ion from the sulfuric acid is still hanging around. Okay, but we're not going to show it in this step because it doesn't really do anything. And now what we have is a water molecule, because we're still thinking about the mixture of ethene and steam and an acid catalyst. So here you need one curly arrow. All right, so pause the video and do that. I'm sure that what you did, if you stuck with me this far, is that, because the pattern here is the same. Okay, so formation of your carbon-oxygen bond. And then here's the kind of twist, if you like, right? In the previous version of the mechanism, we just showed the hydrogen ion, like leaving, if you like. It was just formed again as H+. But it's probably more accurate to think of something else hanging around to take away that hydrogen ion. And you could view it as the negative ion from the sulfuric acid taking away that hydrogen ion, taking away that H+. Okay, so this time we need two curly arrows. The way I've set it up, if you're sticking with this and you're kind of pushing yourself enough, you should be able to suggest what they are. So pause the video and try and do that. Okay, so what we should have is that pair of electrons onto there, just like it was before. But now we're going to show how the lone pair on the oxygen is used to form a bond with that hydrogen ion. Okay, so weirdly, right, what this is going to do in terms of the products is actually highlight the role of the acid catalyst a little bit better. You get your ethanol, and then you get the intact regenerated sulfuric acid, which can act as a catalyst. Okay? Now, weirdly, the role of the ion, the hydrogen sulfate ion, this thing, is actually a base in this step. Again, that's that same logic you've seen before. It's acting as a proton acceptor. This doesn't become a big deal until you're studying acids and stuff in year 13, but it's worth pointing out. Again, if you've stuck with it this far, there's no reason why we can't throw in terms like a base or a proton acceptor. So do you have to do it this way? No, obviously not, because that other version of the mechanism is completely acceptable at A level. This is probably a bit more accurate. It's probably not the most accurate version, right? There's other considerations, but I'm going to not worry about those in this video. There is one more thing that I want to look at, though, which is it's actually phosphoric acid that gets used as a catalyst industrially in this reaction, okay? And now that we've looked at it with sulfuric, we can actually do it with phosphoric as well. So this is kind of, you know, assuming that it's phosphoric acid that we use. The displayed formula for phosphoric acid is not something that's required knowledge for the alkenes topic, but I've shown you it below the ethene. And if you've stuck with everything this far, you should be able to copy all these structures, right, and complete the mechanism, because it follows exactly the same logic as everything we've done so far. Okay, again, if you want to just bow out at this stage, feel free to, but if you've stuck with the video this long, right, then there's no reason why you couldn't have a crack at this. So pause the video and have a go if you're going to. Okay, so I'm just going to whiz through this. So bish, bash, bosh, bish, bash, bosh. There we go. These are all the same movements. It's in one scheme because I've drawn everything really small, but these are all the same movements as what we've had so far. The fact that it's phosphoric acid and that the ion that's formed is a negative ion that you get from phosphoric acid doesn't really make a great deal of difference. So, right, that's it for hydration of ethene. And like I said, the basic, well, the fundamental version was that bit up to when I said, stop now if you want to, okay? And you can just learn that version and you should be fine, right? But again, it's that thing of if you want to push yourself a little further and try and increase the depth of your knowledge a little bit, then this might have been helpful. If you did watch, thank you for watching.